This problem and all other data structure problems can be found here at Sarai Studies. Link is in the description box below. The following array has max heap order. It represents a priority queue, and they're telling us to show the array after one delete max method performed. In other words, we just have to show what it looks like when we delete the maximum key in the tree or the array. First, I'm going to convert this into a binary heap tree, and then we'll convert it back to the array like it wants us to do. I look at the last key, I look at its respective index, and then I know now that I'm going to need 10 nodes. So I write down my first one. I know that in a binary tree, you can only ever have 2 children for each node. So I'm just going to keep adding 2 children for each node until I get 10. So here I have 7, and then from left to right, 8, 9, and then 10. And I like to specify my null length. So here, this is a null, this is null, this is null, null, and null. Then you want to split up your tree into rows or into levels, and then you number. The first one is going to be the one in the first row, and then you move on to the next row because you run out of nodes, and that's 2 and then 3, so from left to right. And then you run out of nodes, so you move on to the next row, so that's 4, 5, 6, 7, and then you run on to the next row, 8, 9, 10. And now to fill in the keys, you already know that at index 1, 16 is going to be in there. At index 2, 14 is going to be in there, so at index 2, 14 should be here. Or you can just recognize that you're going to add these to the tree in order, but by every row from left to right. So then it would be 10, and then you run out, so you just continue the order, 8, 7, 9, 3, then 2, 4, and then 1. Now this is just what was given to us. We actually need to delete a maximum. Well, first you have to recognize what your maximum is. In that case, the maximum is over here, that's 16. And anytime you want to delete something, it doesn't matter if it's minimum or maximum key, you always need to swap it with the last key. So that would be this last one over here at index 10. So we swapped 1 and 16, and now we just delete the last node because that's what we want to do. We want to delete the maximum. We got the maximum to be in the last node, so now we can delete it. So then once we delete it, this becomes null because there's nothing in the left link of this node right here. But then the problem is, remember that after every operation we do, we have to make sure that the property of the tree that we're working with is still satisfied, is not violated. So what's the property of a max heap tree? That the parent is always bigger than both of its children or equal to. So let's look at this. Is this bigger than or equal to both of its children? No, it's actually smaller. So this is an issue. We have to fix that. How can we fix that? By syncing this down. So we just need to swap it with one of its children, but then the question is, which child? Well, think about it. This is a max heap, so we always want the bigger number on the top. So when we're swapping, we might as well swap with the bigger number. In this case, it would be 14. So 14 would go on the top, and it satisfies the condition that the parent has to be bigger or equal to both of its children. So in this case, we swap these two, and then again, after every operation, every swap, every delete, every insertion, we have to check that the property is not violated. We look at this. Is the parent bigger than both of its children? Yes. But then we also have to look at the subtree connected to the one we just changed, and it's this one as well. Is this parent bigger than both of its children? No, one is less than both of them. So again, we have to swap. Swap how? We swap with the bigger one because we want the bigger one on the top. So in this case, we're going to swap 1 and 8. Then again, we ask ourselves, is this parent bigger than both of its children? Yes, 8 is bigger than 1 and 7. But then we also have to check the tree associated with the one that we just swapped as well. Is this parent bigger than 2 and 4? No, it's not. So again, we swap with the bigger number. So in that case, that's 4. Then we check again. Is this parent bigger than both of its children? Yes. So now the property of a max PQ is satisfied and we are good. But they want the array after one delete max. So we have to translate this back into an array. But just to make one thing clear, we sync by swapping with the bigger child. This changes if it's a min heap, and if it's a min heap, it's a smaller child. And that makes sense. Min, small, max, big, so that's a way to remember it. But let's go ahead and rewrite this. So again, we never start with 0, we start with 1. You see 1 here. What's next to it? 14. So 14 goes here. Or you can just literally write the keys in order as you see them in each row from left to right. So 14, 8, and then 10. Then I see 4, 7, 9, 3 in one row, and then 2 and 1. And it makes sense that we started with 10 nodes and we ended with 9. Why? Because we deleted 1. And that's your array after performing delete max for the first time, and I'll see you in the next video.